All right, so chapter 7 is about kinetic energy and work. Now, in the first few chapters, you learn that when you have an object that's moving with a velocity, then given the acceleration, if there's any acceleration, then you can actually use the equations of motion to find out at what time that the object will be where, and the object is moving with a velocity. Now, with the velocity, what we know is that there is an energy associated with the with the object if the object is moving with a velocity, and that velocity energy is what we call the kinetic energy. So what is the form for the kinetic energy? Kinetic energy, we use a symbol capital K to indicate that's kinetic energy, and that's equal to 1/2 mass of the object, and then times the velocity squared. So you can see that whenever an object that has a velocity, it means that it carries energy, and that energy will have the form that's 1/2 mv squared. As you can see, this is always positive, because your v here, your v, whether it's positive or negative, once you square it, it becomes a positive quantity. So you have 1/2 mv squared. That's a positive quantity, and the unit is joules. Okay, so this is definition of kinetic energy. It basically describes when the object is moving at a velocity, then it comes with the energy that is 1/2 mv squared. And there are situations that you've done from chapter 2. You've learned that the object can change its velocity. So how does an object change its velocity? How does an object change its velocity? When there is acceleration, right? When there's acceleration or deceleration, then velocity can change. So you can see that when velocity changes, how does it affect the kinetic energy? The kinetic energy also changes as well, right? Because kinetic energy depends on the velocity. So when velocity changes, it means that there's a change in kinetic energy. So how do we change kinetic energy? By what means do we change the kinetic energy? We mentioned I asked you earlier that how do we change velocity? If there's acceleration, then there's a change in velocity. How do we have a non-zero acceleration? By Newton's second law, how do we have a non-zero acceleration? When the net force acting on an object is non-zero, right? Remember, F equals ma. So when in order to have acceleration that is, in order to have a non-zero acceleration, you have a net force that's not equal to zero. And so in order to change the velocity, we have to trace back to that there must be a force acting on the object, so that the object will have an acceleration, and that acceleration is going to change the velocity, and so accomplish the fact that the velocity can be changed, and of course the kinetic energy will change as well. Okay, so that kind of ties together the relationship between the force and the kinetic energy. Kinetic energy is a constant. It's not a constant. Is a scalar. When I say scalar, what does that mean? It's just a magnitude. It's just a number. It does not come, you do not resolve this into the x and y. So in other words, if you have an object that's moving in two-dimensional plane, if the total velocity is v, then your kinetic energy is just 1/2 mv squared. You do not use 1/2 n and then vx squared and then 1/2 m vy squared. In other words, you do not resolve this vector into the x and y, because kinetic energy is not a vector. Okay, so whenever you're given the velocity, you use the total velocity, the v here, the magnitude, and to calculate your kinetic energy. And we mentioned that you have to apply the force in order to change velocity. So how does that work? How does that force apply in order to change the kinetic energy? So we're going to derive the equation that illustrate that when there's a force acting on the object, there is work done on the object. So when you have force, that force is used to do work, and work can be positive or negative depending on the direction, depending on how the work is applied to the object. And when there's a change when there's a work done on the object, then it's going to change your kinetic energy. Okay, so work itself has a unit of the of joules of the energy. So work also has joules, and if we look at this, let's say joules, that's 1 half mv squared. So we know that 1 joules is also equal to the unit for mass, which is kilogram, and velocity is meter and then square. So you have the meter square and second square. So joules basically can be can be written as kilograms times the meter square over a second square. But most of the time we just use joule. That's a unit for energy. So we're going to see how when you apply a force to an object, then that force is going to do work on the object and in such a way that changes kinetic energy. Okay, so let's see how are they all related to each other. The principle is that when energy transfer to when energy is transferred to the object, then we consider that work to be positive. When the energy is transferred from the object, then we consider that work to be negative. So in other words, when energy is added to the system, which is transferred to the object, then we consider that as the force is doing positive work. When energy is transferred from the object, then we found that the work done by the force is considered negative because it takes energy away from the object. And we're going to do illustrate some of the cases that that with the same amount of force acting on the object, it might do positive work, it might do negative work. It really depends on the displacement as well. Okay, and so what is work exactly? So work is defined as the energy transferred to or from the object by means of a force acting on the object. So in other words, work is related to force, and whether and then the force can do positive work or negative work to the object. Okay, so that's definition of work, and so schematically you can see that this is an object. When this is the direction of work, so this is considered positive. And when it takes away energy, then that's considered negative. So in other words, this object loses energy when you have applied work to extract energy from the system. Okay, so let's see how we relate work, force, and also kinetic energy together. Okay, so let's say if you have an object that's confined to move horizontally, and let's say it has initial velocity. So let's say you have this, and I think in the book it says that you have an object right here, okay? And let's say you apply a force. You apply a force in this direction. So this is the direction of the force, and it's making an angle theta that's right here. And let's say this object initially is moving at the velocity, we call that vi. And then after some distance, let's say after some distance from this point to that point, it moves a distance d, and then its velocity increases to vf. Okay, so these are what we have here. You have an object moving horizontally, confined to move along this straight line. You apply force at an angle that's not directly horizontal. Initially, you have a velocity vi. After some distance, the velocity becomes vf. All right, so let's look at this equation. What can we get out of this? Of this picture. When this object is moving at the velocity vi, what is the energy, kinetic energy associated with this, which we call that initial kinetic energy? So your ki is equal to, This is moving at this velocity. So your kinetic energy initially will have a value of, or the expression of, yes? Exactly, you have 1/2 mvi squared. That's your initial kinetic energy when at this starting point, right? After you move at this point, what will be the final kinetic energy? That will be 1/2 mvf squared. You can see that it's very direct, very straightforward. It's just the applications, just use this equation. Kinetic energy is always 1/2 mv squared. This is initial velocity, so it's 1 half mvi squared. This is the final velocity, so that's 1 half mvf squared. So you can see that your kinetic energy, initial and final, they may not be the same. It really depends on whether the velocity changes or not, right? Okay, so we have that. So now let's look at Newton's second law. Based on this, because from the equations of motion, you apply the force, it moves a distance d, velocity change from vi to vf. What is, by Newton's law, what is the acceleration of this object? Does this object have an acceleration at all? Does it have an acceleration? How do you find the acceleration of the object? When you have a force acting on the object, and of course it has gravity, it has a normal force. So those two in the vertical, they cancel each other, right? So horizontally, what would be the force that's providing an acceleration? Newton's second law, what would be the force? What would be the force? Okay, so Newton's second law says the net force in the horizontal direction is equal to, hold on, F equals ma. You have mass of the object, you have the acceleration of the object. That's how you relate the acceleration to the force, right? So if the object is moving with the acceleration a, so you have ma that we know. What is the net force in the horizontal direction? What is the net force? If you apply force here, and it has the s component, you have the y component. So what will be the s component be? F cosine, right? Because it's adjacent to the angle, so that will be F cosine theta. So you have F cosine theta. That's equal to ma. Any questions so far? This is just direct applications of Newton's second law. F equals ma. Now the F, of course, is not a total force. It is the S component because this B is not moving in the vertical direction. So the only motion is horizontally. So you have F cosine theta, that's equal to ma. Okay? F is considered to be known. Theta is considered to be known. And mass is given, so you have the acceleration. We need to actually, relate all this to your energy. Acceleration and velocity, they are related to each other. Now, if you recall, there are three equations of motion. Which one that relates acceleration and initial and final velocity? Which equation? And also the displacement. What equation? If you remember, what is the equation? Yes. Okay, that involves time, right? Yeah. Final velocity. Okay, so there's one equation of motion that says the final velocity square is equal to initial velocity square, and then what? Plus 2 times acceleration, and then times displacement, right? And the displacement from this point to that point, that is your, what's that? What is that displacement?
D.
That will be just d, right? Okay. So based on this diagram, the final velocity square is equal to initial velocity square plus 2 times the acceleration and then times the displacement. This, and this are all given. Any acceleration can be found by using this equation. So what we're going to do is that we're going to replace our acceleration with this expression. So that before we do that, let's just say that from this, we can deduce that your acceleration is equal to the horizontal component of the force over the mass. I'm just going to plug into here. So what we have here is that the final velocity square is equal to initial velocity square plus 2 times the acceleration, which is the force component over the mass, and then times the displacement. Okay, so this is what we have after we do the substitution. And then what I'm going to do is I'm going to multiply the mass on every term, and then I'm going to divide. Divide 2 on every term. So what we have here is that. So this will become what? If I multiply by n divided by 2, that becomes 1 half mv squared, right? Okay. So what we have here is that you will get, after you multiply m and then divided by 2, you got 1 half mass final velocity squared. And then that's equal to 1/2 mass initial velocity squared. Right? So far, so good. And then there's just, after you do that, so you have your F plus F times D times cosine theta. Okay? So if we look at this expression, we immediately identify that this is, what is this? 1/2 mvf squared. That is your final kinetic energy, right? So we just put down, this is my kf. And then on the right-hand side, I have my initial kinetic energy. So that's my ki. And then we have this unfamiliar terms, which is the force magnitude. Now, and then times the displacement, horizontal displacement, and then times cosine theta. So what we're going to do is that we're going to move this ki to the other side. So I have my final kinetic energy minus initial kinetic energy. That's equal to force times d times cosine theta. What is kf minus ki? That would be the change in kinetic energy, right? So we call that delta k, change in kinetic energy. And that's equal to f times d times cosine theta. All right, so what is f times d times cosine theta? So force is a magnitude. Displacement is a magnitude, force is a vector. D is also a vector. When you have two vectors multiplied together, and then with the magnitude, and then there's a cosine there, what does that tell you? What sort of product is this? Scalar product, vector product. When you have a cosine theta, what kind of product is this? Scalar or cross product? Or dot product? You can pick one of them. Dot product or scalar product or cross vector product? Scalar, right? Why is it scalar? Because your energy is a scalar. So this is equal to that. This must be a scalar as well. And then you have FD times cosine theta. That's a total sign that it is equal to F dot D. Okay? Because F dot D is equal to FD cosine theta. By the way, I thought this would be actually a simple problem on the test. You just use F dot D, that's just FD cosine theta. But a lot of students actually did wrong on the last one, the last problem. They actually went through a lengthy step, they resolved the vectors and stuff. But you don't really have to, because whenever you have scalar product F dot D, that's just FD times cosine theta, and theta is the angle between force and the displacement. All right. So this is the force. This is the displacement. The angle between them is theta. So if you want to do F dot D, then that's just FD times cosine theta. Okay. So what does that tell you? The change in kinetic energy can be accomplished through the force that does work on the object, and that's equal to F dot D. Okay. So it's a scalar product of F dot D, and F dot D is what we call work. Okay, this is the work done by the applied force when you push the object with the force, and when the object is moving at a distance d, then work is done, and work is done by this magnitude F dot D. So it's not just the force magnitude times the displacement. There is also a modification term that's cosine theta. That is because even though the force has two components, the S component and the Y component, the displacement is in this direction. The only term that will contribute to work is the Fx, the horizontal component of the force. This term, Fy, has nothing to do with this. Okay? And that's because if you apply the formula, let's say work is F dot D. You can immediately see that you can use the your D is horizontally and Fy is vertically. The angle between these two forces is, of these two quantity is displacement horizontally and Fy is vertically. What is the angle between them? That's 90, right? So when you do cosine 90, that gives you 0. That's why the the y component of that force does not contribute to work. The only term that will contribute to work is horizontal component, and that horizontal component is in the same direction as the displacement. So when you do, so the angle between them is just 0. Okay? So in other words, F dot D is F. You can say that F, the S component times the total displacement, or we can say that that's equal to F, the total force magnitude times the displacement, and then times the angle between them. And as you can see, when you do F times cosine theta, that basically is just your horizontal component of the force. So they're all, consistent, with each other. Okay? All right. So, any questions so far? It's about how to find work. So work, the important concept that you want to know is that this is what we call the work-kinetic energy theorem. Okay, work-kinetic energy theorem. It means that in order to change kinetic energy, work has to be done. Okay, and then how do we calculate work? Work is when you are dealing with a constant force. This is how you calculate work for the scalar product of force and displacement. Okay. So that is that. Any questions so far? No questions? So let me ask you. So what we know that there's gravitational force. There's, let's say, normal force. How much work, and this is a force, right? Gravitational force is a force. How much work is done by the gravitational force on the object? So same pictures. Now, instead of finding out the amount of work done by the applied force, I'm asking you, what is the work done by this gravity when it's moving rightward? This is the force direction. This is displacement. So what is the work done by this gravity? That will be 0, right? Because the angle between them is 90. So when you do W is equal to Fg dot D, you will have your mg, that's your force magnitude. You have your d, that's a displacement, and then cosine of the angle between them. The angle between them is 90. Okay, so when you have that, that just gives you a big 0. No work is done by gravitational force. And that's because gravitational force is in the vertical direction. And the displacement is in the direction that's perpendicular to the gravitational force. What about the work done by normal force? What is the work done by normal force? So again, if you do this, that will be the normal force, scalar product of normal force and displacement. So you have your whatever force magnitude of normal force times the displacement and times cosine of the angle between them. What would that be? This is the direction of normal force. This is the displacement. Still 0, yes. Okay? Now be confident, it is 0. So because you are using this equation, and this equation also tells you that it is 0 because even though this quantity is not 0, this quantity is not 0, but the angle between them is 90 degrees. So cosine of 90, that gives you 0. Okay? Any questions so far? So I'm